And feel free to interrupt if you have questions.
Hello everyone. And this is very interesting session for us because World Talent Economy Forum, we are now 50th of episodes, and we come up with one of the brilliant software inventors. He is Mr. Bob Frankston, and he has an engagement with, he's from MIT alumni, as well as he has engagement with IEEE, and he invent softwares and different kind of things for Apple, and many interesting things still he's doing. He's actually from his working place right now. So hopefully our audience today, you will get very interesting insight from the software industry. So hello, how are you, sir?
I'm fine. Thank you for inviting me.
Yes. Yes, sir. Can you please introduce yourself? Because when I Google about you, it's a huge activities I find. So, like, hopefully, just introduce your work and everything.
Okay. I'm scared to look at my description of me online.
Okay.
So I'm not sure exactly what it's saying these days because I feel obliged to correct it. But I've had a surprisingly interesting life. By surprisingly interesting, I grew up in New York, in Brooklyn, in the 1950s, and we actually still had horse-drawn delivery in those days.
Mhm.
But I was lucky enough to grow up as computers were happening. So when I first learned about computers, I went and sent my mother to a faculty class at Hunter College, and I was in junior high school in 1963. Um, and it made sense to me. It resonated, but it was much simpler those days. Computers were much simpler in those days, um,
Mhm.
and that really gave me a chance to learn by doing, to grow up with the industry. And so, when people look at all these languages and things now, I see behind them. I mean, I'm interested in the concepts behind them because, when you take, again, I'm going to talk about this whole concept of software. But when you learn like a language like Python,
Mhm. Mhm.
you know to go from Python all the way down to do people know what a soldering iron is these days,
Mhm.
and how it all comes together? And the challenge is to understand both the conceptual view and the physical view and how they interplay. And I also had a chance to grow up as the industry developed in the middle of basically most of the major trends. Um, but what fascinated me, I came into it sort of from a philosophical point of view. Even when I was at MIT, I was never satisfied with how it was being taught. That there was some, and this is what I want to get into. Some powerful ideas behind software, and just teaching the mechanics doesn't even get at the real power of the ideas. So that's why at MIT I would take classes not just in artificial intelligence, but psycholinguistics, in accounting, and I try, clinical decision making. So I try to get a sense of the ideas while still getting deeply into the concepts of software. And by saying I was fortunate, so my first job happened to be on Wall Street in 1966,
Mhm.
and I happened to get a chance to take a terminal home, and use as much computer as I want. So basically, I've been doing personal computing from home since 1966.
Mhm.
And that shaped my view of computers because in those days, and again, I'm getting a little ahead of myself, computers are thought of as giant calculators. And you'd put data in, it would produce a calculation, you'd print out results. That was the view. Um, Actually, I should have got to the prop. How many people know what a punch card is?
Now everybody is trying to utilize it.
No,
Punch
but
card.
nobody knows. Do you know how we used to write programs? We got a piece of cardboard and we punched holes in it.
Mhm. Mhm. Yes.
People, can't imagine that today.
Yes. Yes.
But what meant you could see everything and understand it. But I was fortunate enough to get a chance to use what are called in those days were real time systems. Prototype today is online and everything. Back then, before most people were aware of its existence. And because I was on Wall Street, I also got a very jaded view of finance. I was in the underbelly, so I saw how things operated and these ideas. Then at MIT, I was in the Multics group. Now, I don't know if the people heard of Multics, which stands for Multiplex Computer Information System. So there was a group that split off because they didn't get their funding. They decided to do a toy version of Multics. Instead of Multiplex, which is Multics, they called it Unix. And you might have heard of Unix. So I saw the birth of all this, and that again, it's a pragmatic background that gives you an understanding. So I can see the magic in this, but I can also see how it works underneath. So it gives me some insights. And then another thing you're going to get into is watch how the internet happened from the beginning and the ideas. But let me back off to really talk about this thing called software and how it was discovered. Now there was this idea called von Neumann computing, because originally people were building mechanical calculators. And again, without props, it's hard. People might even not know you used to make calculators with gears and everything. And then in order to do calculations, people started wiring them up together. And one of the big breakthroughs was what are called von Neumann computers, where instead of wiring the instructions in, you would interpret some numbers as instructions to do the data processing. And it was a clever idea, but it turns out to be a very powerful idea. The idea that the program itself was data. And people didn't appreciate it fully because initially computers were basically giant calculators. So there was a language called Fortran, which was basically, the days of computers were used to do calculation. A lot of it were ballistic tables. During the wars, people, how far do you do something? How do you compute tangents and sines? And they used to have rooms full of what were called computers. A computer was a person who did calculations. And it would take a lot of computers. So having a machine to do it sped up the process. And that's really one of the forces that drove computing. But so the von Neumann computer was one part of it. And a lot of it is intertwined with the history of telephony, because if you go back to the history of how we communicate, the term telecommunications was invented in the 1700s. Napoleon had a telecommunications system in France in the late 1700s. It was semaphores, and you would signal one, pass the message on and on. And and it was modeled at the post office. You were carrying messages instead of the messenger, carrying point to point. With the postal, it would pass it on. With the telegraph, you did that electronically. So that's really the design point of our telecommunication system. You think of telegraphy. Again, I'm using these terms. How many people even know what a telegram is, or a telegraph? Or Morse code, you have the key clicker. And one of the big breakthroughs was the talking telegraph. You might know of it as telephone, of course.
Yes.
And it's interesting because they were basically treated it as a series of telegrams, that the way you billed for using the phone was in terms of message units, at least in the United States. A message unit basically was a telegram. So the phone call was treated as a series of telegrams for the billing system. And that's the way it was viewed. Today we call those minutes, but it's the same fictional creation. But the problem you had with analog systems is preserving the signal of the message, because the telephone system took responsibility for carrying the message all the way. And in order for it to work, you had to have precise coordination, because you basically had a microphone at one end and you had the speaker at the other end, and you put a long wire between them. But the longer the wire, the noisier it get, the harder it was to understand. And it was very expensive to maintain the system. So the telephone industry in the United States had a lot of money to spend on research because it was protected from real competition. And in the U.S., it was the FCC. Other countries had the PT&Ts, and they all followed the same model, which was basically government-controlled industry. Whether there was in the U.S., we had AT&T that was government-controlled and protected. Other countries might have had more direct government control. But AT&T's research division, Bell Labs, did a lot of research. How do we reduce the cost of telephony, improve the quality? And they came up with this idea of digitization. You would sample the signals, and you would, instead of sending the analog waveform, again, okay, the challenge here is finding the right language, because when I talk about things like analog waveforms, I've got an electrical engineering background. If you don't have it, it sort of, had to preserve sort of, if you look at the graph, the exact signal. By sampling, it was now digital. And digital signals had the wonderful property, especially when they're just 0 or 1, of regenerating. If the signal became fuzzy, it's 0 or 1, you can regenerate it. That means that, unlike, in other words, if you whisper something to somebody and they don't quite understand you, it starts to fuzz out as you go further. But if you know they're either saying 0 or 1, it's easier to regenerate it over distance. And that works very well. And suddenly you can take this phone signal, and instead of it generating, it became possible to keep the quality up over any distance. And the phone system actually didn't become fully digital till the 1970s. But the ideas go back to the 1930s. And the problem is that, well, as with any new technology, it was done in substitution mode. In other words, it was done to emulate the old system. You would still bill for phone calls. Everything was just like the old system. And the digital phone system had to reserve a path for that signal and take the resource away and assign it to that one call. But just backing off before I get to that, so I don't know how many people heard of Claude Shannon. What he did was come up with this called information theory. Now, one of the great tragedies was he chose the word information. And that word, now I don't know how many studied physics and entropy. It was a synonym for, or reverse meaning of entropy, which was as you try to maintain a system, it gets a little fuzzier and fuzzier over time. So entropy was a measure of the disorder. So information theory took an abstract mathematical model, says, if we contain the signal in this channel, we can then measure properties of it. It was totally artificial, just like any, when you teach physics, you have an artificial model. You don't take into account all the factors. You have a very theoretic model. So information theory was a very theoretic model. Had nothing to do with what people mean by the day-to-day use of the word information. Nothing to do with speech. It had to do with, once you've encoded the signal, here's how you handle it in this very artificial environment. So one of the first problems was, because he used the word information, people thought he was talking about day-to-day speech. So the analogy I use is, if you talk about work, you don't pay people by the amount of, the term for work in physics, ergs. You don't ask how many ergs or how many foot-pounds or things like that. You pay salary based on the contribution or the competition. People don't confuse the term work in physics with the day-to-day term work. But people confuse the technical term of art of information with the day-to-day use of information. And we have a complete policy based on that confusion. Even today, we're told, that Claude Shannon says there are only so many frequencies of colors. So the other part of this now, and these trends are going to pull together, is how do we communicate? So when you carry a postal message, you're trusting somebody to carry the message. Now, that if you wanted to basically, if you were speaking, Mandarin, and you had an English speaker carrying the message, they're not going to. They don't know it's important or not.
Exactly. Yes, yes.
So this is why I preserve the waveform. But there are limits. You don't know what's important, so there are limits. I mean, and the telegram was interesting. That the telegrams had to be in English because we couldn't do the coding, Bordeaux coded things were all around English, which caused a problem. You couldn't really get the nuance and everything. So it was a naive view of how we communicate. It was a view of communicate as opposed to people. When you have a conversation, you have concepts and ideas you exchange. You don't have the information is not in just the message. Matter of fact, one example which shows the problem of applying information theory to speech is how much information is there in a pause? If I stop speaking for a while, there might be a world of information there, but it doesn't fit into this artificial model. But the telecommunications policy is still based on the idea the meaning is in the wire, the value is in the wire, because that's all we can do. We can pass it along. So these trends, so one of the, just taking the telephony thing and then we bring it together, is in order to preserve the signal, we need to have a channel. Originally, that was a wire. We dedicate a wire to a single telegraph message. Now, as an aside, Alexander Graham Bell was supposed to do the harmonic telegraph to put multiple signals on a wire. He was badly behaved, didn't do what he was supposed to do, and played with this idea of voice instead. But that's a whole story in itself, and a lot of it's local around here. So this idea of preserving having a preserved channel in order to preserve exactly the waveform, in terms of isochronous, keep everything exact, was brought forward as the basis for the telecommunication policy. Sort of like a railroad. You reserve a wire, you carry the message as freight. We even took it to the point of creating artificial wires by dedicating frequencies, radio frequency, for each message would have a dedicated frequency. That was in the 1920s. That was the best we can do. We can basically electronic tuning forks, harmonic signaling. So all these come together. So we have a telecommunication policy based on reserved channels, including dedicating frequency bands. And the theory, again, justified by misunderstanding of Claude Shannon, is there are only so many frequency bands you can allocate, and the government has to license them. So all these are coming together to form modern telecommunications policy. But the byproduct of that research was the idea of digital technology, software. And that's where we get to the von Neumann machine I mentioned earlier. That took that digital signal but did it very differently. So instead of just using that digital signal to carry the messages, it was now used as the base of computation, and all that technology for processing it allowed us to interpret it as instructions. So in 1958, John McCarthy basically came up with this idea. And there was a whole group of people talking about artificial intelligence, a lot of psychologists who were upset at B.F. Skinner left Harvard to come to MIT. Including J.C.R. Licklider. I don't know if anybody have heard of him. Mm-hmm. He was an acoustic psychologist. Mm-hmm. So they wound up at MIT. So one of the trends was John McCarthy came up with a language called Lisp processing language, which was intended for AI. But it had a very different view from the standard calculations. It treated each of those numbers as symbols. to try to mimic sort of what the brain does with symbolic processing and everything. And turns out that that is really much more powerful than treating them just as numbers for calculations. They had no intrinsic meaning, and that was very powerful. Now, I don't know how many people have heard of Lisp, but Lisp, there's a version of Lisp called Scheme, and JavaScript was based on Scheme. So those ideas have come back in the form of JavaScript. So people think of JavaScript, as this is quickly designed language. The reason it's quickly designed and it had some issues is it was based on this long tradition of symbolic processing, and that's why it actually turns out to be an amazingly good language these days, especially with versions like TypeScript, which just give you assistance. And Python overlaps with this. I think Python doesn't have quite the same heritage, but a lot of the ideas are similar, especially now that Python has type annotation. All these features come in. But you notice Python is not just about calculations, it's about data, it's about processing information, lists, all these concepts have come together. But so as I said, I grew up in the 1960s when we were starting to play with these computers, and it wasn't just, again, for the calculations. I was fortunate enough to be working in online services, so we're actually creating software for normal people to use. So in May of 1973, I found myself at MIT. I was already working professionally for many years in this class where we studied packet networks. So radio packet network. Think about a radio packet network. It was a hack. People had already had the idea of computer networks. It wasn't just the ARPANET. There was also private networks and everything. They'd have packets and something. So a lot of these ideas were very common. And as an aside, Lickladder shows up because he's the one has Intergalactic Computing Project who helped give us the ARPANET, which funded it. He also helped fund Multics project. But remember, he was an acoustic psychologist. His goal in all this technology was to enable people to communicate and work together, not just do computation. And it turns, this idea that it was acoustic psychology also comes up again. But so I'm in this class where we're studying computer networks. And we're studying what it seemed like a network in Hawaii called the Aloha Net. It was really just basically a bunch of researchers, kids, who wanted to do their own connect the computers together. So they had some radios, and they had to relay the radios. But the problem is that the problem with the radios is sometimes things get garbled. You lose packets. So what you did, you have a computer. You lost a packet, fine, retransmit it. You could program around the lack of having a provider. Now, in those days, we thought of it as a network. Okay, but and in fact, the kid next to me in class, how many of you know who Bob Metcalf is? He was the kid next to me in class.
Yeah.
I came up with the idea of putting a Aloha net on a coaxial cable as the ether. So you might guess what that became. Ethernet. Now, I don't know how many people know all these terms and background you can research, but basically, the Ethernet was just a packet network on a wire. But it was not, what I came to appreciate later, I'll get ahead of it, is that the Ethernet was not a network, it was just a coaxial cable. We use the term, and here's where language keeps, so this is where it's all self-referential. We're talking about how we communicate, how we use language. And understanding language is part of understanding the misunderstandings behind today's policies. So when we use the term network, everything is a network. We have social networking. It's like confusing, arranged marriages with social meetings and everything. That's all. The words allow us to speak past each other and fail to communicate. Matter of fact, the word As I point out, the telecommunication department is not in the School of Communications. We use the same word, but we confuse the two. And again, the policy confused the two. In the US, the Federal Communications Commission tells you what words you're allowed to use. That's the speech commission. So we have all this confusion going on. But the importance of Aloha Net, to me, is it was the first example where I discovered the idea that you do not need a provider to guarantee the message gets through. And this idea fed into the Internet Networking Project. Now, you might have heard of it. Familiar with the Internet
Yes.
Networking Project? You know what it's called today.
Mhm. Yes.
Yeah, the Internet, obviously. Now, the Internet Networking Project was interesting because it did not attempt to do traditional internet networking. Because traditionally, if I had my phone system in this country, you had a phone system in another country, we had to make sure the two protocols matched. And that never really worked that well. The national phone calls are delayed, and if you did video, forget it, because they're getting all those formats to work together. Now, what was interesting about the packet networks, and I use, but people aren't familiar with LoHaNet, we'll use the Ethernet as an example, is all you got were packets. There were no, you didn't know whether the packet was part of a video conversation, was voice, was it image, or what. So the Internet Networking Project basically didn't even try to do traditional internet networking. All it did was exchange packets. And the term, I know people familiar with the term best efforts. What best efforts means is you didn't guarantee the packet would get through. You just made your best effort. You didn't purposely not carry it through. And what is surprising is how well it worked. Because in the 1970s, when the project first started this approach, it wouldn't have worked for voice, but it was good for email. And because you didn't know what kind of packets it had, you basically couldn't do any special favors. So you had to only do it, worked at the edges, and it was fine because it was a free resource. Since you didn't know what the packets are, you couldn't charge for them. So in the university, if you plugged an Ethernet cable here and you plugged it to another university, once you interconnected them, things would just work. It was very simple. Now, interesting question is, why did it work? It worked for the same reason. Remember when, again, I have to realize it's been that long ago since people had very noisy analog cell phones. But why did those work so well, even though they were so terrible? It's because you can say, you repeat it, explain it. Now, also a good student will ask questions. They won't pretend they understand the answer. The bad students will pretend they understand. The good students will tell you, I don't understand, please explain it better. It's a conversation that drives it. So one of the reasons that this approach worked so well was it was a conversation. You were able to ask what things meant and clarify them. So even if you lost a few packets, that was fine. You had a conversation, you correct for it. Now, what is surprising is how well it worked. And one thing you discovered is all these things about, well, before I get to the whole thing about phone calls, one other aspect was you didn't need a reliable path. Let's say you wanted the latest temperature. Let's say you lost a reading, it didn't matter. You just send the next one. That sometimes the policy of better never than late worked. So streaming, if you lose a packet in streaming, in the old days, you'd have a big clip. You couldn't do that. You had to make sure it all worked. And what I was getting to this before is that streaming works now because we can program around the gaps. What's surprising is that voice over the internet works. Now, why does it work? Well, it turns out one of the byproducts of the university system with open availability was research at CERN. Tim Berners-Lee basically was able to do this little project to use a protocol, which again, I can give you the history going back to the MIT in the 1960s, called HTML and runoff, and he came up with HTML and access protocol called HTTP. There were things before that called Gopher, but and then you had researchers who basically developed the browser with graphics and everything, and just built on these. And it was not contained; it was an open. You're asking, how do economies do? This was technology made available to all. You can call it basic research, or just call it. It basically created a resource for society available. And as the web grew, uh, the more we can do with it. And at some point, the odds of packets getting through became high enough that we can do voice. Now, the surprising thing was voice over IP had to be discovered. We had been doing voice over Ethernet in special cases where we can guarantee the capacity reserve with digital networks. But with voice over IPs, it works without promises. It works because we can accept that sometimes it doesn't work. That video, I remember the World's Fair in 1964, seeing a video phone, a picture phone it was called then. And it was a marvel, but it never caught on because it was too expensive. It was too expensive, but it had the guarantee it would work. By removing the guarantees, accepting the risk, and sometimes the call would be fuzzy, sometimes it wouldn't get through, it became free to use. And that's remarkable because the web had created the capacity. And then we discovered we can do voice over it once we have the capacity. It's that indirect process that makes it very hard for people to understand that it wasn't because we meant to make it work. We discovered it could work. But we have the habit of confusing what we discover with what must be. So this is why I get to the idea of how can we get more of an opportunity. But let me back off a little first on getting back to the software and digital, because that's the real big idea. That software is language of, I call it understanding. It's the way I'm understanding how brains work. So one of my big influences was Seymour Papert, who looked at how do people think, how do children learn. He was a student of Jean Piaget, who studied developmental psychology. So this seems, far afield for computers and stuff, but it's actually central because you're looking at how words work, how people form concepts, is vital, how we organize our thinking. And part of it is understanding why those symbols I mentioned John McCarthy came up with, why symbolic processing was so important, why AI is important. And one of the powerful ideas, which we really haven't come to terms with, is that those words do not have intrinsic meaning. Where do the meaning of the words come from? And that's a difficult concept because the meaning is not intrinsic. The meaning only exists in the whole, not in the parts. And understanding software gives us an articulate understanding of that. And why I say, reality is digital, why we have quantum at a low level, is because otherwise things just become undifferentiated. By digital, it basically gives an organizing principle for understanding our knowledge. And this is not just about computers. Do you know what other system is digital? One of the things very close to our heart? DNA.
Yeah. Okay.
Okay.
Yeah.
The same principle.
Okay.
We're just apps.
Okay.
And, it's not just that we descended from monkeys, I think. We're just apps. Basically, by visual instruction, expression, but geology, this is a fundamental principle. And if you understand software, you start to understand how public policy, for example, how we basically create wholes out of parts, why you need a community, why individuals in isolation are meaningless, because the more detail you get into, the less meaning there is. So we need to balance societal policy with individual policy. We tend, the way I put it is, business books were written by lottery winners who tell you how to choose the numbers. because you don't learn anything from success. You learn anything by looking at the whole. What failed, what didn't, and then how do you share that success and how do you make it available to others? So, how do we create an environment for discovery and exploration? So, the internet is a laboratory for this. That because the numbers are meaningless, we can take those packets we exchange and do anything with them. We don't have to know what they mean on the wire. What's interesting is if we encrypt the packets and send them by all different means, the conversation, it exists here, it exists where you are. It does not exist in the middle. It does anybody in the middle, it isn't there. Now this idea is very powerful. For example, Amazon uses it. So if you order from Amazon, you have Amazon delivery in Malaysia? I don't know.
Yes, yes,
Okay.
yes.
And if I order a toy from Amazon, it does not get shipped from Seattle.
Mhm.
For you, it would get shipped maybe from Kuala Lumpur or some other city. We send the
Mhm.
bits. We don't send the physical object.
Mhm. Mhm.
So if I order, so my mother once asked me to send a toy truck to my nephew in Seattle, and I was in New York. So I told her he's gonna have it in 1 hour, and he did. Now, how did I get a toy truck from New York to Seattle in 1 hour? I give you a hint. I did not have a hypersonic ballistic, missile. I simply returned it to the store and gave my brother the part number, and he bought it the same part number. The trick is understanding that that's the same truck. That's an example of understanding this philosophical concept and how we can leverage them. We're still just at the early stage. We call that logistics. We treat each of these as a special case. But this is a new resource, so we're creating an abundant resource. So the phone network in the United States in the 1990s was about to collapse. Everybody was staying dialed up, often to AOL, and tying up phone lines. Suddenly the crisis disappeared because we chopped all those calls into packets, and packets allowed us to take that Y, which shared one call, and made it a shared medium for many calls. It was no longer dedicated. You no longer got a busy signal, but somebody's using that wire. It became a common resource. So all these ideas come together. The fact that packets have the means we don't need a special network for each purpose. We don't need separate facilities. We start to create abundant capacity because we can now share it all as abundant commons. And anybody can create anywhere. So, VisiCalc basically gave people a tool to do a lot of financial calculations in a way without going to process. It leveraged individuals in the context of society. So how do we get more of this? So obviously we get more understanding, more education, but the one public policy we can do is what I'm calling the public packet infrastructure. Today we have a telecommunications system which requires basically everybody subscribe to a subscriber, and the value is not in any wire, so it doesn't make any sense. Instead, we need basically open connectivity, just like we have roads everywhere. And you don't need the roads. People understand. I can get from point A to point B without a road. It's just a lot more work. Roads are just facilitated. They're not fundamental. Unlike railroads, which you had to buy a ticket, roads are just a resource. I can take a dirt path. I can take any mixture. It's up to me. I can decide to take a bus. So you create the opportunity. And the public packet infrastructure, based on the same principle as the internet, enables us to do all these new projects and ideas, like education in the United States, especially now, and the rest of the world. But we have a crisis here. People need to be able to go to school from home. That's an indirect stakeholder. You can't say first you need to subscribe to this, you need to afford this. It's got to just be there. Same for telehealth and telemedicine. Same for just about anything. We can now basically, instead of building a physical system for each purpose, we now have this powerful common resource. The transition we're going through now is, people worried about capacity. And yet, I mean, think about it. We casually assume video conferencing or Zoom everywhere. I mean, just a few years ago, think if you try to tell somebody, not only we're going to have a phone system, we're just going to casually have video conversations. It wouldn't have made any sense. So we have the abundance. We just don't realize it because we're locking it up behind old policies. But we also need to accept the other ideas that we don't know all the answers. We have to basically create opportunity for discovery. And then a policy, in other words, you don't say you're not allowed on the sidewalk until you prove yourself worthy. You basically have policies of behavior separate from how you use the sidewalk. So we're still coming to terms with this. We're also coming to terms with new threats. We used to feel safe because the people who scared us were far away. Now they're everywhere. There's no separation. So we're going through a transition, learning how to use this. We have to find the balance between sort of embracing these new ideas, experimenting with them, and surviving them. And there's no one answer. We can't just put a wall between what's good and what's bad. We can't hide behind the wall cities. And a lot of governments come to some are clamping down, saying we don't want any new ideas. Others are much more able to embrace new ideas. And we go through these phases. Now we're going through a phase where we're afraid of everything. But now the world is being forced to change. And now we're going to sort of, the side benefits of a calamity is that there's a chance to reinvent. So we can't waste this simply on just bringing back the old normal. We have to discover, the new possibilities and embrace the opportunities. So I think that's a good stopping point. Can I have people ask questions, tell me what they're interested in. I can explain things in more detail. And one thing in education, one more. Our education system needs to catch up because we're still teaching people facts. And this is one other lesson from Seymour Papert, is we need to teach people how to learn. He introduced, I don't know if you ever heard of Lego building blocks, Lego language. That was Seymour Papert. And the purpose was not to teach people a job skill. Programming, not as a job skill, but as a language for understanding. Just like you use Python as a tool, the software as a language for understanding and for how to learn. If you don't understand something, it doesn't mean you're stupid, just debug your understanding. So these are part of the concepts which are transforming. It's going to be a while before, they're really appreciated and understood. We have a whole legal system based on good or evil being inherent as opposed to operational, et cetera, et cetera. So let me open to questions.
Yeah, there are some specific audience response. I will go there. Before I go there, I have a
Look at
specific.
live comments. It's a live comments.
Yes, yes,
Oh, sure.
yes. So basically, sir, I just want to know, like example, you work for many brilliant projects. Especially, we are very interested how you work with Apple and their
Well, I
invention.
didn't work with Apple.
Yes, yes.
I worked with Dan Bricklin. We happened to choose the Apple II computer first.
Mhm.
And you can look at, I think they were almost about to go bankrupt, and then we turned their toy computer into a business computer.
Mhm.
And I very much appreciate Steve Wozniak's
Mhm.
attitude. He created the Apple II, but he couldn't not create it. He was fascinated by the project. He didn't necessarily have a purpose. He wanted to play with the computers. And I think a lot of it is driven by his interest in exploring. And with VisiCalc, we basically, it was discovered, here's a tool you can use. It wasn't a sort of plan for that. We discovered the match. Dan Bricklin was at business school, was frustrated by all the calculations. We both had extensive experience by that time. And this is where you get the innovation. Dan was in the class. He had the idea. You should look at his TEDx talk on the invention of this. That previously, probably we had to name everything carefully. The idea could point to something. In fact, we had an interactive screen. We were able to rethink it because he happened to be working on word processing online systems, and thought through sort of the user experience. But VisiCalc was not a program; it was a product. We were trying to create an experience. We were facile enough with software that we can focus on the experience we were trying to create rather than on just making it work. So I think, okay, if the user was doing this, press this. So it worked very hard. For example, we didn't, it was now, how many people know how small the Apple II was? So we used to computers, maybe 32 gigabytes. This was 1/1,000th the size. It was working less than a megacycle, so it's like a 1/1,000th speed. So this is trillions of times less powerful than today's computer. So we had to be very careful and leverage everything. We didn't have room for error messages, so we had to have all interactive in order to get feedback right away. But the key thing is we were using software as a tool, and the other part of it, though, is we're not giving people a calculator. We're giving them a tool to explore ideas. We're giving them a way to do programming. So VisiCalc basically gave people a way to tap into the power of the computer, not just to do calculations, but to work out ideas. And the experience with Apple is, I don't know how much I appreciate it fully, but they came up with, they would use it for inboards and outboards. One of the product managers came up with a very clever project management system using VisiCalc. He later went on to Apple, where he was in charge of the Office team. And so, not bad for a farm boy from Nebraska. So a lot of people, it was, embraced the ideas and understood to varying degrees. So I'd follow Apple over time. And I also was aware of the work at Xerox PARC, which Apple based its Mac on. But I was never directly involved in Apple.
Thank you, sir. Basically, there are some specific audience response, but I have actually a lot more questions to you.
Okay, ask.
Maybe we have to extend. Yes, because when we start our discussion, you said that you needed decades of discussing all of your work. Very interesting. Very interesting. Mohammad Sohail Rana, he said he's actually doing a lot of job for us. He's our teammate. He said, great discussion, Mr. Bob. Would you tell us what is the impact of cultural difference on communication in distributing software development? Humaira Tanzila, I'm just following their...
I see it over there. I see. Yes.
Yes.
Distribute TED. First, is interesting language. Interesting. I think there are a couple of factors. One is people have to learn to play together, to cooperate. And while I don't always agree with Richard Stallman, I think this idea of open source, that we often do better by sharing the effort than competing on it. We have to decide sort of where do you add value and where do you contribute to the whole. So the value of things like the Linux project and others is that people contribute to the commons, just like in your city. You can do things on your own, but you also contribute to the city infrastructure. And I think software as infrastructure is a very important part of this. So that's one aspect of distributed development is that there's no magic. Each project does need a leader and everything. It's interesting, if we go back to the Multics project, the one that gave birth to Unix was done in this style. That everybody contributed, look at the other person's code, that would criticize the other person's code, not to compete, but because they wanted to contribute to the whole of the project. And Fernando Corbato, who unfortunately died recently, his great achievement was not the technical achievement. It was a managerial achievement of getting all these people to work together to contribute to the project. And it's interesting, it was a Project Mac, which was run by J. Shar Lickletter, who also did the ARPANET project. So at that point, we had another advantage. We had a small community, which was concentrated in one place. So you could walk down the hall and talk to people. We also used email. I mean, if you want to go to dinner, you send email to the guy in the next office. Walk over. But at the same time, those personal relations are very important. So one of the challenges these days is how do you do distributed software and form the personal relationships without being in the same place? So there's another aspect where people get it wrong, and I'm calling the 737 MAX problem, is when you outsource development. That doesn't work if the team, I mean, you can treat a couple of programmers just, okay, do your job, don't contribute. But what you lose is the interaction. In other words, the programmer saying, "Oh, I did this. There's an opportunity here. You can build on this." Or, "Oh, you asked for this. You should have asked for this because now that we're doing, we understand this." So it's often hard to maintain that when you're too distributed. So you need to have a spirit of cooperation and contribution. So how that varies culturally, I think it's also something to learn that each culture has a degree of how do you cooperate, how do you add to the whole. But you also need the ability to push back. That if I criticize your code, you shouldn't take it personally, unless it is personal. But you need the ability to say, okay, here's a better algorithm. Doesn't mean you did wrong. Is I happen to have this experience which did. So it's very hard to escape the cultural assumptions that it's personal. It's very hard to escape the cultural assumption there's one right way to do it. One of the things that the aviation industry discovered was some of the crashes were caused by pilots being or co-pilots being too respectful of the pilot, not criticizing them. So you need a culture where you can stay engaged and that it's okay to be wrong and disagree, and except there's no one right answer. So how that plays out varies, and I think it's a big transitional thing. Like this open packet infrastructure is still hard to do culture for a lot of reasons. So I don't think there's one answer on that.
Okay, there are some other audience response. Humaira Tanjila, she said, "Hello, sir. We are glad to hear from your valuable thoughts. Thank you." Firdaus Rana, she also gave you thanks, and she said, "Do you think in COVID situation people are getting enough support from medical software?"
Well, there's a lot. The whole area of medicine, it's a long time. I did spend time in that world, and is a problem of hierarchies and respect. I think medical software, we need to figure out how to do more. We're trying too hard to build complex systems, record management or something, and I think there's still a lot of room for exploration and experimentation. So I think at the earliest stages, my son got into neuroscience because of doing software, in the medical world. Um, so the short answer is we're just at the beginning of we're doing too much to deal with the bureaucracy and actually make it worse for now. That a lot of doctors are spending more time fighting the computers than treating patients. So we need to have much more of a consumer software attitude in medicine, ease of use, freeing up doctors to pay attention to patients instead of filling out insurance forms. So I think we're at a stage where software is providing a lot of benefit, but it's also, I think, making medicine more difficult. So, uh, but I think we need to learn how to be sort of more agile and versatile while still understanding, people's lives are at stake. So I don't have an easy answer except we're just starting out the process with the early stages. And actually, I will give one more example where the packet infrastructure makes a difference. That we're now forced to do what's called telemedicine. What is telemedicine? Uh, from Cisco's point of view, telemedicine is remote surgery. That's telemedicine should be more mundane. It could be a video conversation like this. I remember I had a rash once. I didn't want to go to the doctor. My doctor, that one wasn't that technical, but a friend of mine knew both of us. So I mailed him a picture of the rash. He said it to my doctor. He said, "Oh, it's just this." So a lot of the telemedicine we have to recognize is mundane. A lot of things don't need visits. A lot of it is just simple connectivity. And in particular, compliance in medicine. So one example is we have these watches. This is not a best example, which can do medical monitoring. But we don't take advantage of it because we don't have a public packet infrastructure, which means that connecting each device becomes too complicated. We go to a new place, we have to reconnect. It's called onboarding, or we have to pay for subscription. We have to get. That's why you don't see a lot of it. So once you remove the barriers, I think we're going to see a lot of experimentation with simple mundane medicine, where we just provide like compliance, healthcare. The danger, though, is the number of scams might go up much faster. But we also might get more internationalized medicine. But we don't need somebody diagnosing you, locally. It could be, we have different levels of care. So we have some certifications here. We got first level triage taking place anywhere in the world. We One reason I think we have a lot of doctors from other countries in the U.S. is being a doctor in the U.S. is a terrible profession. It's a lot of work. They said the kids don't do it. The new people come in, and fortunately, the world is full of brilliant people, and U.S. benefit or used to benefit. I won't get into the politics too much, but we'll soon be able to tap into the talent more out throughout the world by taking advantage of these technologies. So that's not a very specific answer, but there are just many ways in which we have to do it. It also gives a better understanding of how systems work. Biology is a terrible place to do science because it's too complicated. One of the reasons I talk about digital systems, and if you look at our body, you have organs, you have all these digital things, which mean sharp distinctions and systems, and we're just beginning to understand that too. So we're at about, I say, within another 200 or 300 years, we're going to have a handle on it. I hope sooner. I want the benefits.
Yes, this is very interesting discussions. And side by side, I just want to understand in present situations like many of the company develop a lot of softwares, and many startup company also developing softwares, and many of them actually 100% not successful for getting the result. Like they are failing. Many of the startup right now they are failing, and
Yeah, but that's
yes.
normal. The startups are supposed to fail. That's why I create startups. I mean, we have. This is why it's so important to have a safety net. And normal countries, unlike the U.S., have like medical care and things. So if you fail, you just start up again. I mean, the U.S. strength has been if you're bankrupt or the concept of bankruptcy. Okay, you start again. You get a chance to start again. If you can assume you have health care, you can take a risk. So it's fine for startups to fail. That's a unit of evolution. You fail, you start again. So, but the thing is, you have to remember, software itself is a tool. You don't create software; you use software to do something. Some software you create tools like compilers and processors, but for the most part, software is our new building blocks. Basically, software is the way we make things. We don't necessarily do physical things. Well, you need more physical building blocks. I've got a lot of little devices like these, which I can just place somewhere. It's got a software interface. I can now build a temperature monitor system. I can just throw these around, and now I can figure out what the weather is over an area. So we're just learning how to use these tools, but a lot of the efforts can fail, but still deliver value. And we need to be able to try ideas. And this is what I was saying before. We need to tolerate chaos and survive it. And then so we have a chance to discover new ideas, but we can't predict them. And so that's why failing software is fine. If we learn from it and you get to try again. The problem right now is we have a finance system like venture capital, which tries to capture all the value. The web wouldn't have happened if they tried to capture the value and did let people invent using, building on it. This is where the open software and the sharing aspect. So how do we find the balance between people benefiting from their inventions and sharing so that the 99% of the people who fail get a chance to try again, and the 1% who accidentally succeed recognize that some of it, they deserve to be rewarded. They won the lottery, but much that goes to society and should be shared. So let's embrace the failure rather than saying it's bad.
So one specific things in recent years, we find a lot of involvement with AI and blockchain technology. So
Okay.
yes, yes. So issue is that how we can integrate it more with this kind of technology,
Okay.
how it works.
So
Yes.
first, when I hear the word blockchain, I say, unless you explain to me what you're doing, don't use the word blockchain. Okay. because it's take on magical things. So what is AI? And this goes back to, you know, I studied, you know, Marvin Minsky.
Mhm.
So those are the people I've studied with. And Papert and Marvin worked together. And so I looked at, you know, all the various threads of AI. One is trying to understand how people work. Another part is machine learning. Now we have to be very careful about machine learning. Now, in a sense, it is part of AI because our brains there's some similarity. But you have to understand that it is nothing magic there in the sense of it's trying to find patterns. And how do you find patterns? Well, there's no one algorithm. You can train it, you can have look at enough patterns, you can find it. Sometimes you look out. I use the example of the solar system. You're familiar with Copernicus. He saw a pattern, whereas people looked at the sky from the Earth's center, he saw all this complexity. He saw a pattern called the solar system, which isn't a physical thing. It's a pattern people saw, just like they used to see constellations in the sky to find patterns. Now, machine learning is based on finding patterns. It's not necessarily like the brain. And it depends on basically concept like locality, the ability to sort of look at a small number of things and infer a larger pattern. Those are arbitrary patterns. They're not magical. And they're often perverse. In other words, you can find ways to fool them because you have two things that humans see the same. Machine learning might see them very different because they're picking up on clues they can't explain themselves. So machine learning is a tool, but we have to be very careful to understand what it is. For example, uh, this is a societal policy thing. Let's say you're renting to somebody and they have an arrest record. That's not a conviction record. Machine learning will tell you don't rent to anybody with an arrest record. But think of how that reinforces prejudice. If you look like somebody the police pick up, you suddenly can't do it. And this way you get the stereotypes of racial discrimination because statistically you can argue it, but that's based on false analogies, not individuals. And the danger is with machine learning is we reinforce our misunderstandings and our prejudice rather than challenging them. So you have to recognize machine learning is a powerful tool, but at the same time, it can mislead us because the pattern might work against the larger society. Yes, they corrected the small, but we need to have societal policies that challenge them. Now, blockchain, there's Bitcoin, there's a magical thing. It turns out when people say blockchain, which blockchains? Distributed ledgers. And most of them are not fully distributed because it's a lot easier to say, okay, I trust somebody. They're trying to do trust with zero trust, and that doesn't work. It's the same with security. There's no trust. Again, one thing I say is the people you trust with your life, but not your money. That doesn't fit into a simplistic model of you're putting security walls around things. And the other problem with the Bitcoin algorithm in particular is it actually doesn't work. Bitcoin market can be cornered. There are ways to cheat and everything. So people are looking for magical answers, and if they don't understand the limits of machine learning, they don't understand what a blockchain algorithm is. And the problem of it's a very central. It's a decentralized, centralized. It doesn't work if the parts are separated. So it becomes a very vulnerable and problematic settling time. So people keep saying blockchain is the answer, and they keep searching for the question of answers. So we should learn from it how to distribute ledger, how to do. Uh, and one of the things is OAuth. You familiar with OAuth? It's an authorization where you get an authorization token. That builds on the idea of numbers being meaningless, so it can give you a token. So it's really, you have to understand the ideas behind this, not take these as this is sort of the magic tool. They're really just algorithms and tools that we have to be very aware of and understanding what they are. So when you do data mining, you don't say, okay, I've discovered this, the data tells me to do this. No, the data is the data, and you have to bring adult supervision to it.
Yes, so this is very valuable thoughts. And what do you think? Like in present situation, there is a competition in between human and AI. What will be future?
It's not a competition.
Mhm, mhm,
I mean, AI, it's sort of AI. you're worried about intelligence taking over. Well, first, let's separate machine learning from AI and the self-awareness. Okay. Uh, if the AI is that powerful, why would it? This is a discussion we had back in the '60s. Why would it care about us? It would go do its own thing. We're competing with resources. No, they're just two so very different modalities. Does it need us for food? I mean, yes. If you watch The Matrix, the secret is we're lousy batteries. So I'm not worried about AI. I'm worried about humans thinking AI is magic. I'm worried about, and we've had this. People basically look for the one right answer. They look for the authority they believe in. They keep looking for, what's the one, and then they punish people who have the wrong ideas. And we've had a history. Sometimes those, imposed ideas work for a while, but what's missing is the ability to challenge or reinvent. And if people foolishly accept, oh, the machine told us to do this, the algorithm told us to do this, well, that's a problem. We need to go the opposite. Right now, we have a legal system which does not have these ideas. A legal system based on good, evil, and it's not context sensitive. And we have to accept the fundamental intrinsic ambiguities. There isn't good or evil. There are contexts in which things work better and things work worse. So it's not AI the problem the people.
Understand. No, this is very valuable discussion because World Talent Economy Forum, we are trying to find out the real answer. And
There is no answer. There are a lot of questions.
Yes. Sir, there is an audience response. I just want to share with you. He's Arak Mehraj. He's also working with our team. He said, Mr. Bob, thank you. I think after COVID pandemic, the users of software may increase in all areas. Do you think in that case, there is a possibility of starting unhealthy competition among the software development companies? Because you have to understand, he's from South Asian market. So here is a huge populations and a lot of people actually trying to do work with softwares and a lot of misleading.
Again, software is a tool. Okay. It's not a thing in itself. And one of the problems we have, like hackathons, they give a false idea that, we'll just sell this problem in isolation. Everything is isolated. Well, no, things are part of systems. They're connected. We have to. One of the important things is not in the software itself. We have to think about the questions we're asking, not the answers. In other words, we have to rethink what the problems we're trying to solve, and that's the thing. So I think a lot of people say, "Oh, I'll learn to program. I'll create this thing. I'll get rich. I'll choose the right numbers." No, it's basically a tool. It's tool use leverage. Think about what you're trying to do with it. Some of it, like I'm more into the internal where I'm building tools to people use. So how do we create, as I said, if we have a public packet infrastructure, which you think of it as Wi-Fi everywhere with no sign-ons, no subscriptions, things just work. Now, what can we use software to create? And yes, there will be competition. I'm not sure what unhealthy competition is. It might be a winner take all, where one person wins, everybody loses. What you need is one person wins, everybody wins less well, because the winners' great winnings are shared by the community, which keeps trying, as opposed to software we're trying to sort of, make the other person lose.
Yes, sir. In recent years, we are getting to the 5G network. So
terrible. 5G is a disaster. 5G is an attempt to bring us back to the 1970s or before. 5G has every bad idea of telecommunication rolled one. Now, let's be careful. There are 5G radios, which are fine technology, which is also the same technology as Wi-Fi 6. That's fine. The problem is the 5G network protocols are trying to have one goal, only one goal: kill the internet. Because when we create software in our devices, when we do conferences like this, they don't get any money for the video calls. They want to say some things are special. You need to build a network. Yet I've not seen a single important use case of 5G that justifies have the whole protocols. They give remote virtual reality. You don't have a crisis of virtual reality. They're going to telesurgery, which I call murder. But if something goes wrong, it fails. All these things require more the internet style connectivity. More important in terms of policies. I'm going to get to this. Public packet infrastructure owned locally. Telecommunication requires you have a national provider can make promises, can reserve capacity, can sell it to the highest bidder. A public packet infrastructure owned locally. You own your local infrastructure. It becomes a local resource that you use to create your solution. So first, you have the benefit it's owned locally rather than to a provider. And then it becomes a resource you can use to invent the world. You don't need to coordinate, you can discover. 5G is the opposite. 5G says someone must own it all, must take it away from you so they can sell it to somebody else. And they create scarcity by saying this wire is now dedicated to this one person. So the purpose of 5G is create scarcity, bring value back into the network. And it also has the idea that now once it's in the network, they can tell you what messages are good and what messages are bad, and basically eliminate innovation. They can limit and make it too expensive to communicate. They can kill education and all these telehealth because you have to negotiate with every carrier. And they're not adding value. It's called rent seeking. It brings back, you have to pay off a phone company. You cannot innovate unless they make money. So 5G is all of those rolled together, and there is absolutely no reason to have it. If anything, there's a reason not to have it. It also adds complexity. All the lessons we've learned about how to build systems with the best efforts, they're going back to the days to failed ideas. When there was a program called ATM, asynchronous transfer mode, never really worked between carriers, but it's too complicated to make it work. So 5G is all those bad ideas rolled into one. So you really want to go. We have a similar problem with TV. There's a more complicated protocol called ATSC, Advanced Television, whatever it is, because they didn't believe the internet would ever work well, and they're trying to roll this out. Turns out, with all the streaming and everything, working well. What problem is 5G solving? 5G solves one problem, which is bringing the money back into the phone network and kill all this silly internet stuff. Now, it's wonderful in countries that want control. And this is one reason why China is going to have problems, because as much trouble have in the U.S., at least we embrace the idea of open connectivity and everything, and you allow for innovation to try to survive it. Countries which are afraid of this are going to have problems, because a lot of the innovation in China has been because of the chaos. As you remove the chaos, you remove the discovery. So it's going to be interesting how this plays out in each country. I think India is chaotic, which gives it an advantage.
So a few other things now working with for the smart city, let's say VR.
Another bad idea.
Okay, okay. VR, AR, as well as IoT. So what's your concept on this?
Okay, a lot of the terms we lose. So let's look at IoT. What is the Internet of Things? I read a lot of papers, and what people usually mean by the Internet of Things is taking their old ideas, dust them off, get a little stamp that says now with Wi-Fi, and they have all the old principles. So I hesitate to use the term, even though I used it giving talks. But it really is about embracing its best efforts, connectivity, ad hoc connectivity. So I can take a device like this and make it available to you without building a special network, without engineering. It's this ad hoc connectivity and discovery. And what is there is the fact that we're now having these devices that connect to the physical world that are open connections. This is why a company called Shelly.cloud, if you go to this site, has nice building blocks. And I think we're going to have to get more companies that are giving us open building blocks rather than smart ones that limit the ability to innovate. But we're going to have to do it safely too. So it's a process, and which brings to smart cities. The problem with smart cities is I don't want a smart city. I want smart people.
Yes,
so
brilliant.
In the U.S., there's a story of Robert Moses. And it is called Power Brokers. So what he did, he basically and he wasn't alone, but we have a lot of examples of this, where you build the city, where you make the city, we'll put build the businesses here, we'll put the highways through the slums, we'll rip them down, we're going to make it like it never worked. So because it was all pre-planned, it was careful, it took all the energy out. There's something called Jane Jacobs, who looked at how do people interact. And basically said, well, you mix them up, you give them a chance to get together and discover. And Jane Jacobs has become the model for cities that where you have business and living and all these things mixed together, the different communities together, and you give a chance. And one reason I like to visit New York, you get all these what are called ethnic communities, but you find these different communities that juxtaposition, mixing and overlap. There's some irony in Toronto, where Google's Sidewalk project, which is a smart city project, got kicked out. Toronto is the city that Jane Jacobs loved as a vibrant city. So this is why I talk about the public package infrastructure. If you assume this is a resource for a city, we can now make the people smart, the city smart. So two examples. One, when you look at, I remember going in Cologne, seeing a trolley schedule on a board, and I realized the value is not in that schedule. That data was available if I want to use Google Maps or other tools, or Train City Planner, all these schedules. It empowered people to add their own value to the city. So an empowering city gives you the tools, it gives you information. The train schedules get an APIs, and anybody can write software to basically do planning. Anybody can write software to do their own environmental monitoring. And it reduced the cost. Instead of spending $1 billion on an all or nothing smart city projects, almost all of which fail, we can now basically build a common infrastructure with which low risk, and then people can do things like a train schedule map at very low cost and make it available. And each of those adds value to the city. They make the city more valuable. The key is to understand how to empower people to use software to improve the city, how to add capacity to connectivity to the city without having somebody doing it all or nothing in the smart city.
Yes, this is very.
One of the other things I remember talk on how slums become cities and the process, rather than planning, how the people learn to work together slowly. They build infrastructure. It's not a perfect process. It does help to have planning. But those are examples of how they become vibrant environments. I mean, it's amazing if you go to some of the slums. People do live there, and it's, I grew up, I wouldn't call it a slum like another city, but you learn that, you don't need this fancy, shiny city. And those are areas which become exciting and interesting. Yes.
This is very interesting discussion, sir. Definitely in the future we're going to invite you. This is very interesting discussions for us. My last questions for you, like, what do you think how we can build better softwares and software companies, especially?
Well, I mean, right now I'm enjoying JavaScript. My next comment, setting pointer, is on the JavaScript ecosystem. So JavaScript is interesting because it's giving us a chance to basically make software more accessible. It makes it easier to transfer software, interconnect software. JSON, which you can use in Python, basically becomes a way to exchange data. And it's nice because we worked hard to be efficient and everything. And by relaxing, we discovered that we can embrace these new ideas. So that's one of the trends, is basically making software simple, more accessible. In other words, we're not using software as this rigid building block that's precompiled, carefully doing. This is more flexible, and we're learning how to do this. So JavaScript, as I said, brings back forth some Lisp ideas, and some see a lot of Python too, and it's shifting the way we think about software. But we have to remember, software is a tool, it's a language. It's not the product itself. And I think that's really, one of the misunderstandings. What really is important about software is a tool for thinking and understanding. And a world in which we used to think that you either did something directly or indirectly. Well, it's becoming blurred because you can make things happen by having software as your agent, We're learning how, if two people have rule sets, how do they combine? In other words, this is a problem with smart cities. I think about this in terms of smart homes. Home automation, which is a term I hate. So you give a room for how the lights work. Well, first you don't know how to debug it. So you can discover one day and you wonder why the lights are flashing. Well, it's rule. So that's why learning. And if you live with somebody else, their rules, in the real world, you just accept that you're not going to get exactly what you want. We're learning how to do that in software. So we're learning how software is not this precise engineering tool. It's simply a way of encoding some of our ideas some machines can execute, but they're not executing them in isolation. They're executing them in context. They're interacting with other software. So, there's no magic, but I think the JavaScript ecosystem shows you one direction ahead. But we're also going to need to learn how to, like a legal system. Our laws should be written more like software. And one of the challenges is how to preserve the ambiguities. One way our legal system works is it preserves some ambiguities, leaves leeway. The same in good software. It doesn't try to lock everything down. So how do we take the language of software and apply that to society more general, to societal rules? And we also need, bits are like money. They're just concepts. And we need to learn how to work with the ideas.
Thank you, sir. This is actually brilliant discussions today, and actually, what our promise from WTE Forum, we want to unveil the truth. We want to bring all of the. It's all about experience. You have a huge experience, and you come up with your experience, and you try to share. Even let's say Mohammed Sohail, he said, through the discussion, we got a lot of important information that will be a great use to us. He's also trying to develop in software. So this is the way that how we can get like your knowledge, and we can explore ourselves. This is right the way, the feedback from the industry. So this is our target actually, World Talent Economy Forum. We try to bring all of the brilliant people in our forum, and we have to connect each other, and we love to learn, and we want to explore, and we want to contribute. So we need more of your support.
I'll close by saying, beware of brilliant people.
Okay.
They're people with some interesting ideas,
Mhm.
but you have to also think for yourself, and that your ideas are valuable too. And a lot of what seems like brilliance is luck.
Okay. Definitely, hard work also important in your age. You are doing hard work in your
I'm
office.
having fun. I don't do
Yeah.
hard work. I have fun.
Very good. This is the spirit. I also learn. Always I say to my family that when I work, it's actually fun.
Yes.
So same thing. Yes.
And it's a privilege to be able to have fun. Not everybody has that option. So I'm very aware of sort of my luck and my privilege. And it's important to be aware of that and not confuse your success with that you deserved it. No, you were lucky. It was not fair.
Yes. Thank you, sir. Thank you, sir, for your valuable time. And World Talent Economy Forum, definitely in future, we will invite you more. Your
Yes,
valuable
I
time.
look forward to traveling again. I've got a lot of airline
Yes.
miles to use.
Yes.
But
Definitely.
it's a
Definitely.
very different world.
Yes. Definitely. We will arrange a summit, conference, and many more discussions. We will invite you. And this is very valuable discussion today. We will learn more from you. Thank you, sir, for your
Okay. No,
valuable
I
time.
appreciate the opportunity. Thank you.
Thank you, sir. Thank you.